It refuses to move. You turn the bottle upside down. You wait. Nothing happens. You tap the glass. Still nothing. Then suddenly, with one sharp shake, it breaks. The solid vanishes, and the ketchup flows abundantly. Toothpaste is the same. It squeezes out like a liquid, yet sits on your bristles like a solid. So what is it? A liquid or a solid? These familiar materials reveal something deeper about the nature of matter. Something that connects your kitchen to collapsing dams, earthquakes, and even sinking ships. Now imagine that same behavior not in a bottle, but across an entire landscape. On January 25, 2019, in Minas Gerais, Brazil, a massive structure failed. A tailings dam holding millions of cubic meters of mining waste had stood still for years. From the outside, it looked like solid ground. It looked stable. Then, without warning, it collapsed. What followed was not falling rock or sliding debris. It was flow. A thick, heavy wave surged forward, engulfing everything in its path. It moved like a liquid, dense, dark, and unstoppable. The Brumadinho Dam disaster killed 269 people. Entire ecosystems were buried. Rivers were contaminated. A landscape was reshaped in minutes. Something that behaved like solid ground had transformed into a surging mass, and then, just as quickly, settled back into a solid. How can something that looks like a solid suddenly start flowing like a liquid? To understand that, let's look at materials like ketchup, toothpaste, or mining mud. These are not normal liquids. They are called yield stress fluids. You can think of them as materials with a built-in threshold. This graph shows how they behave. On the vertical axis, we have stress. That means how hard you are pushing on the material. On the horizontal axis, we have shear rate, how fast the material is moving or deforming. So imagine a pile of mining residue or thick mud. Its own weight is pushing down, but if that stress is still below the yield stress, it just sits there, stable, not moving. But if the stress increases enough because of added weight, vibration, or disturbance, it reaches that threshold. And at that point, the material starts to flow. Why does this happen? At a microscopic level, the material has structure. The particles are connected in a network like a fragile house of cards. This structure traps the liquid inside and gives the material its solid-like behavior. As long as that structure holds, the material resists movement. But once the stress is high enough, the structure breaks. The particles rearrange and the material begins to flow. Now look at the curve. The steepness of the curve tells us how hard it is to make the material flow faster. At the beginning, the curve is steep, so it takes a lot of extra force to increase the flow. But as the material starts moving, the curve becomes flatter. That means it gets easier and easier to keep it flowing. This is called shear thinning. That's why ketchup is hard to get out of the bottle at first. But once it starts, it pours easily. In large-scale systems like mining tailings, this behavior can become dangerous. Once the material starts flowing and its resistance drops, it can move much more easily and much faster. Now scale this back up to Brumadinho. The mining tailings were a dense, yield-stress suspension. For years, they appeared stable. But deep inside, the physics were shifting. Water pressure within the material was rising. As the water pressure rises, it pushes the particles apart. The friction holding the house of cards together weakens. When those contacts can no longer support the weight, the structure fails instantly. This is static liquefaction, a sudden, violent transition from solid to fluid without a single tremor to warn you. A similar mechanism happens during earthquakes. But before we go further into this strange world where solids can flow like liquids, take a moment to support the channel. If these ideas spark your curiosity, hit like and subscribe. In many cities, the ground is made of loose, water-saturated sand. Normally, the grains touch and support the weight of the world above. But when an earthquake shakes the ground, the grains try to pack tighter. The water trapped between them has nowhere to go, so the pressure spikes. Grain contacts weaken, and for a few terrifying moments, the ground behaves like a liquid. Buildings don't just fall, they tilt. Roads don't just crack, they dissolve. Sand and water erupt from the surface like geysers. In this laboratory experiment, a box is filled with sand saturated with water, water that sits between the grains, known as interstitial water. At first, the grains are in contact, forming a connected structure. Even with water present, the sand behaves like solid ground. It can support weight. The box is then shaken to simulate an earthquake. As the shaking intensifies, the pressure of the interstitial water increases, pushing the grains apart. And then, suddenly, the structure collapses. The grains lose contact, the sand loses its strength, and the ground liquefies. Objects on the surface sink, while buried structures like pipelines rise due to buoyancy. In 2010 and 2011, a series of earthquakes struck the Canterbury region of New Zealand, devastating the city of Christchurch. The most destructive came on February 22, 2011. It killed 185 people and transformed large parts of the city in seconds. But beyond the shaking, something even more destructive was unfolding beneath the surface. Large areas of Christchurch experienced severe liquefaction. The ground itself lost its strength. Homes tilted and sank. Cars were partly swallowed. Roads fractured, warped, and collapsed. Entire neighborhoods were buried beneath thick layers of sand and mud. In some districts, the damage was irreversible. But what exactly happened beneath the city? Beneath Christchurch lay water-saturated sandy soils. Even though water filled the spaces between the grains themselves remained in contact. The ground still behaved like a solid. It could support roads, houses, and entire neighborhoods. Then the earthquake began. As the shaking intensified, the grains were forced to rearrange into a denser state. But the trapped water could not escape fast enough. Water pressure inside the soil rapidly increased beneath the surface. As water pressure continued to rise, it began to balance the weight carried by the soil itself. The stress rose above the critical threshold. The grains lost contact, and at that point, the soil no longer behaved like a solid. It behaved like a liquid. Liquefied soil could no longer support structures. Buildings sank and tilted. Cars became partially submerged. Roads cracked, warped, and collapsed. Sand and water erupted to the surface, transforming streets into unstable ground. When the shaking finally stopped, some of the water slowly drained away. But the damage remained. The soil was left in a loose, weakened state. The ground settled unevenly, and structures remained permanently damaged. Across Christchurch, liquefaction affected vast areas of the city, causing severe destruction to neighborhoods and infrastructure. Entire districts became uninhabitable. Thousands of people were forced to leave their homes, and more than 8,000 houses eventually had to be demolished. The cost of rebuilding reached tens of billions of dollars, reshaping the city for years to come. The Canterbury earthquakes became one of the clearest modern examples of how liquefaction can turn solid ground into a source of catastrophic destruction. Liquefaction can also put ships in danger. Bulk carriers transport large quantities of mineral ores, such as nickel ore, iron ore fines, or bauxite. These materials are not solid rock blocks. They are mixtures of fine particles in water, with mechanical behavior similar to other yield-stress materials. During a voyage, a ship is continuously subjected to waves. This produces repeated motion of the cargo inside the material. This cyclic loading can increase the pressure of the water between particles. As pore pressure rises, grain contacts weaken, following the same physical principle. If the moisture content is high enough, the cargo can lose strength and undergo liquefaction. When this happens, the cargo is no longer a stable weight in the hold. It's a shifting tide. As the ship leans into a wave, the liquid ore flows to one side, creating a weight displacement that destroys the ship's balance. If the tilt becomes too large, the ship may capsize. Tragedies like the MV Vinoline's Queen and the bulk Jupiter have been linked to this exact mechanism. This is why shipping regulations are so strict about moisture. A cargo that looks bone dry at the dock can become a lethal liquid at sea. The triggers may differ: a collapsing dam, a shifting tectonic plate, or the rhythm of the waves, but the underlying physics is identical. The line between a solid and a liquid is not always a sharp boundary. It's a spectrum controlled by stress, structure, and motion. From a bottle of ketchup to a collapsing mountain of mud, the same rules apply. Sometimes what looks like solid ground is only waiting for the right conditions to begin to flow. Thank you all so much for watching. Your support means everything. Don't forget to like, subscribe, and turn on notifications so you never miss a video.